I'm Alice Harpole. I'm a PhD student at the University of Southampton, where I am doing computational astrophysics. So I'm going to talk to you about kind of an experiment that I've been doing the past few months, trying to build a Python front end for some of the high-performance computing, HPC, high-performance computing codes that I've been using. Okay, so why did I want to do this? So basically, the code that I'm using is done a lot in Fortran and C++. And lots of stuff is done in Fortran. And my first language I ever learned was Java, so Fortran for me is just really rather counterintuitive because it's not object-oriented programming. Surely that's the only way you can program. And I've had so many issues with Fortran arrays not numbering themselves from 0. Like you can start them from -10 and it will still work, and it's insane. So basically, I wanted to write a bit less Fortran and a bit more Python. I wanted to try and simplify debugging. So lots of these Fortran issues have been really hard to solve because if you go over the end of a Fortran array, you won't get a segfault like you do in C++. It will just continue running happily. And then you'll come back a few days later and realize that everything is complete nonsense. So I thought with Python, it should hopefully be simpler to debug. I wanted to make some nice plots. So Python has loads of amazing plotting libraries. So I'm going to tell you a bit later about one that I've been using. And I wanted to smooth my workflow. So I'm running my code on a supercomputer, which means I have to submit jobs, and I have to write job submission scripts and stuff like that. So I wanted to write some Python scripts to try and make that a bit smoother. Okay, so a bit of background about the code that I'm using. So I'm using AMReX and Astro. So AMReX is an adaptive mesh refinement code. Basically, it takes some kind of physical system, it puts it on a load of grids and does calculations. That's all that is. So it was originally called boxlib and was written in Fortran. And then gradually they're starting to try and re-implement it in C++. But unfortunately, all the underlying data structures are written in these things called fabs. Which are some weird thing called Fortran array boxes. It basically means anytime you do any direct computation on the data, it's all in Fortran. So then Astro is a code that sits on top of this, and it's used to model astrophysical flows. So I'm using it to model oceans or neutron stars. And it uses AMReX to do the adaptive mesh refinement, so all the clever trickery with grids and stuff. So again, all the higher level code is in C++, but anytime you do any data manipulation, so anytime you're doing any kind of like maths and physics on the actual numbers themselves, it's all in Fortran still. Okay, so this is what I've done to try and make a Python front end for these codes, and what I'm going to be talking about for the rest of my talk. So I have wraps in Fortran using a library called F90wrap. I've embedded some Python in C++, so I've called Python from C++, and I'll let you know how successful that was. I've done some prototyping, and I've used Python to help manage job submission. And finally, I've done some plotting. So a little disclaimer here, this is all just some experimentation I've done, and I thought other people might be interested in. There are probably much better ways of doing this. If you do know ways, I'd really love to hear about it afterwards. But yeah, I am not an expert in this is just my experiment. Okay, to start with, so I wanted to call Fortran from Python and C++. So when I'm setting up my problem, I have to define the kind of starting state of my problem in a load of Fortran functions. And these Fortran functions are then called by C++ wrappers. So what I wanted to do is instead get these C++ wrappers to call Python functions. Now, this might sound a bit weird because I'm doing high-performance computing. It needs to be very fast. But these initial data functions are only called once. So if they take 2 minutes rather than 5 seconds, that doesn't matter because my code's going to run for a few days. So if it's in Python, I can modify these files quite quickly, and I can spend a lot less time debugging them, hopefully. So this is really quite an attractive proposition for me. Unfortunately, there was a bit of a complication that I found when I was doing this. So the Fortran modules that I was calling, they relied on other Fortran modules which had something called Fortran-derived types. So yeah, so basically this is what I wanted to go from. On the right, you don't need to read this, I just wanted to show the size. On the right, I've got my Fortran function. Sorry, on the left, I've got my Fortran function. So it's got a horrendous amount of stuff at the top defining all my imported modules, then all the types of my arrays and everything. And this is what I condense it down to in Python. So it's a lot less verbose and a bit nicer. Okay, so in order to wrap this stuff, I use something called F90 wrap. So F2Py is something that I'd used previously when I was trying to optimize my Python code. So it's a really great utility which allows you to wrap Fortran function and then call them from Python. And so yeah, it's like pretty magical. You can just immediately call Fortran functions. F90 wrap then builds on top of this and allows you to support modern Fortran, which has derived types, which are basically Fortran 90's version of classes. So when you run this on a module, it will produce you Fortran 90 wrapper files, which you can then compile into a Python extension module, and it will then provide you with a high-level Python module with a lovely Pythonic interface. Okay, so let's see an example of this. So here I'm going to define just a really simple Fortran module. So I've got a type I've imagined called F-type. It has some integer and some float in there. And I'm also going to define a subroutine, which does a really simple computation on this type. So it takes the mantissa and it raises it by the exponent. So really simple Fortran module with a derived type and a function. Okay, so let's compile this. So I'm first compiling my module, and then running F90 wrap, and I'm then kind of compiling my wrapped Fortran module to produce a C extension. So it does a load of stuff, spits out a load of output, and then hooray, it works. So let's see what this Python module looks like. So we can see here we've got a class, which then has, this is my Fortran derived type in here. It has a lot of spacing in these wrappers. So it's got my properties, so it's got the two variables in my derived type here. And if we look here, it's also got my function. So let's try calling this with Python. So here I'm just going to import my module and then define some Python function which will set the two things in my derived type, and then it will call the function on my derived type. So let's run this. Hooray, it works. Sure, it's not a fluke. Let's change a number. Different number. Hopefully that means it's working. Okay, so it's possible. However, I had a bit of a problem when I came to testing this, because in my code, my Fortran function was relying on variables, global variables, which had been set by some other Fortran functions. Nightmare. And so one thing I could have done is I could have wrapped all those Fortran functions, but that, to me, seemed like I was just going to go down a rabbit hole and it would never end, and I'd end up having to wrap basically 1,000 Fortran functions, which sounded a bit annoying. So instead, I used a patch. So I used unit-test.mock.patch to mock the Fortran function, so I could just test my Python code in isolation. And when I did this, I'd never done this before. Now I have done it. I'm going to use it everywhere. But yeah, basically you have to be really careful with the order at which you import things, because Python doesn't re-import modules. So if you import a module, then you import a module which imports that module again. It won't re-import it. That is probably more complicated than I made it sound, but here's a little example. So I've written a little unit test here. So I've got a little mock for my derived type and a mock for my Fortran function. And then I've got two tests here. So one which patches these modules and functions, and one which doesn't. So if we run this using PyTest, we can see the first test, it has indeed called my mock functions. Second one, I've got no printout, so it means that it's been using the native ones. If you notice the thing that I mentioned about orders of imports, I don't import this module until I've done my patches. If I import this first, then it won't re-import these. It won't mock them. It will use the originally imported one. So that's what I meant about order of import being important. Okay, so basically to conclude this small section, I used basically F90 was surprisingly painless. You can really wrap modern Fortran quite easily. And it can be like, I have found no bugs with this. So my code was like, it had an insane amount of external dependencies, like hundreds of files, and it still seemed to work once I got the linking fix, which was a bit fiddly. So I would recommend this if you want to use legacy Fortran 90 code and kind of want to have a nice Pythonic interface. Also, if you want to optimize Python code, then I've found with other projects, this is like really great. Okay, so the next step is I wanted to call this Python code from my C++ wrappers. Now, surprisingly, or maybe unsurprisingly, I couldn't find much information on the internet about this. So lots of people tend to call C and C++ from their Python when they want to optimize their Python code. But clearly not many people want to do it the other way around, because why would you want to slow down C code by calling Python? Well, I did. So I soldiered on. So from the Python 3.6 documentation, it tells you that if you want to do this, you have to have some interface code. And it needs to do the following. So it needs to convert all your data values from native C types to Python types. So it needs to convert everything into a Py object. We then need to perform a function call to our Python interface using these converted things. And then we need to convert everything back from our Py objects to our C data types. So in practice, this means we need to call these things. So to convert our data values, we do stuff like PyLong from long. So this is converting integers, PyFloat from double, so converting floats. We then call our function. So our function becomes an object. So we call that object to return an object. And then we have to convert back. So whereas this was from long, it's now going to as long. So these are converting back. Okay, so on to another example. So here I've written the most complicated Python code ever. So I'm just adding a couple of numbers. And I'm going to try and embed this in C++. So I wrote a wrapper. And unfortunately, it's not quite as simple. So a few things that I'm going to draw your attention to here is at the start, we have to initialize our Python interpreter. And at the end, you'll see I have to finalize it again, so basically shut everything down. We have a few of the conversion things that I mentioned. So we're converting a string to some Py object here. We are here, this is build value. So this is basically converting a couple of integers into a Py object. We have to, before we do anything, we basically have to turn everything into a Py object. So here, before we can even load our module, we have to convert the module string name into an object and then import that Py object. Gets very complex very quickly. And here's our finally, we're actually calling our function. Amazing, after all this work, we finally call it. And then we get the answer back, and it's actually quite simple at the end. But yeah, you'll notice there's a lot of junk in here. So we have a lot of these things called PyDecref. So whenever you create a Python object, it basically increments a reference counter, and at the end you have to dereference everything. So this is a bit annoying, but unfortunately it gets even worse than that, because if you create a reference from an existing reference, it turns into a borrowed reference. So it means you only dereference one of them, you don't dereference both of them, which is very unintuitive. But yeah, it can be done. So let's see this, let's compile it. So I have compiled my wrapper, and then let's call Python from C. So I've added 2 numbers, and I get 10. Again, sure it's not a fluke. Let's put another number. Hooray, I've called Python from C++. Amazing. Okay, so yeah, again, testing is not great for this. So bugs in Python code will produce segfaults, which is quite annoying. And there are you don't get that lovely helpful error messages that the Python interpreter normally gives you. So you basically have to be really careful and explicitly catch all your errors in your wrapper using things like PyErrorCurd, PyErrorPrint, stuff like that. So it's really important to unit test your Python code as well in isolation to really stop those segfaults happening. Okay, so my conclusions on this is that it's very, very fiddly to do, especially if you don't want to go into low-level stuff. I found a load of really, really crazy random bugs with global variables and stuff, and it's a bit horrible. Reference counting is a complete nightmare and just really unintuitive. When it works, it's amazing. You go do all that work and finally it works. It's pretty neat. But basically, I think it's kind of more trouble than it's worth. I'm not really sure that it was worth all the time I spent crawling over all the scant documentation, but it can be done, which I didn't know before. Okay, so quickly here because I'm running out of time. So basically, what I do is I submit large jobs to an HPC cluster, and these jobs will typically run for a few days. And what I find is that if I make a small typo in my initial data or my parameter files, it can sit there. I will spend a few days waiting for it. I'll come back, and then it didn't even start executing because there was a bug. So what I started doing is I started writing Python scripts to do what I like to call prototyping. So it will basically take my initial data scripts and make a much smaller version of the problem. And then it will run that locally on my machine, and I can very quickly see if my initial data's got bugs in it. And I found it's a really powerful thing to do with Python. Also, what I'm working on at the moment is trying to write more scripts to write job submission scripts for me and to submit these and then report back to me when it's finished. I have also started doing a bit of kind of benchmarking, so trying to use Python to estimate runtime from these smaller versions of my runs. And I've been finding this just incredibly useful. Okay, so again, very quickly. So what I really love Python for is plotting. I've been using it from day one. I've just been plotting everything in Python because I was first taught GNU plot, which is disgusting in my opinion. Sorry, we shouldn't say bad things about other languages, but it is nowhere near as lovely as Python. So in previous projects, I've been using matplotlib, and this is really powerful, but this code spits out a custom data type, data format, which matplotlib cannot read natively. But fortunately, the authors provided a plugin for a library called Whitey. So Whitey is an open source visualization toolkit. It has lots of documentation with examples, so it's pretty easy to start it and get going. It's mostly been used in astrophysics, but you can use it for other scientific data. So a bit about what Whitey does is it loads data in things called data sets. It represents your quantities as things called fields, and you can combine these to do all sorts of cool things. And it will also analyze data for you. Okay, so a little example here. So this is what I like to think of as Whitey Hello World. So I'm loading in a data set. This is actual data that I did with one of my codes. And then I'm going to create a slice plot. So it takes my 3D domain and does a slice for it, and then plots out this field here, so my primitive density. So it does that, spits out some stuff, and whoo, we get an amazing plot with very little work. Okay, so to show you that it can do some other cool stuff, I've just put in a load of random functions here. You can all see there's not very many functions here, and with very little work, in my opinion, we can get out a load of really cool stuff. So it can plot quiver plots, it can find maximum values of things and annotate them, stick in timestamps. So basically, it's pretty powerful. Okay, rush through my conclusions. So basically, I found F90 wrap is a really powerful, great utility for wrapping modern Fortran. So you can call Fortran from Python with pretty little work on your part. Embedding Python in C++ is possible, but I don't really think it's worth the time unless you have a really good reason for it. I found Python to be really useful for prototyping my HPC code and checking all my initial data and all my parameter files for me so that I don't waste time sitting around waiting for stuff to run only to find that it errored immediately. And finally, I used a library called Whitey for plotting my custom data type, and I found this to be really quite powerful and quite nice. Okay, so thank you for listening. Be happy to answer any questions.
We've got a few minutes for questions. There are mics built into the room, so if you just manage to speak up and then keep your questions nice and brief.
Did you look at tools like Python and Python 11 to do the work you're doing with the API directly is very good. There are tools like Fortran right now directly. Did you look at those?
I didn't actually look into this specifically. I tried like a load of different tactics, and I mean the functions, like the Python functions I am embedding, are fairly simple. So I mean I managed to use pass arrays back and forth. But yeah, definitely I think if I was trying to do anything more complicated, then I wouldn't want to go through all that. So yeah, as I said, this was just an experiment.
How come C++ was chosen as a higher level language?
So I mean, it's just what the standard is in my field. So in my field, most people use Fortran, like probably 90% of the code is in Fortran, and then
being the low level, but I didn't understand why they chose C++.
it's not the high level, it's just they're kind of steadily converting all the Fortran into C++, and they started with kind of the outer layers of the code. So they're kind of starting from the outside and moving inwards, probably because that's slightly easier. But yeah, it's not seen as the high level.
Have you experimented with any of the Python hydrocodes, like pure Python-based?
Yeah, so I mean, I have been using a code called Pyro, which is basically a Python version of this code, and I write a lot of Python hydrocodes myself. But yeah, and I've kind of run other people's ones. But yeah, this is, unfortunately, I'm doing kind of a relativistic simulation which needs 10 levels of adaptive mesh refinement, so Python is not really going to cut it, unfortunately. Okay, at the back.
Because it goes both ways. You can call Python from C++ and C++ from Python with very, very neat interface. So really my question is going to be, how you looked at that? If you want to bring this to the ACCU conference and propose a small workshop on this, I'm sure there are lots of C++ people coming to solve the problems for you.
Yeah.
And the call is open.
Yeah, I mean, as I said, when I tried Googling it, I just couldn't find much on people having done it this way. There's like all the information about like Cypher and stuff, which I've used before for doing it that way, but doing it the other way, it seems to be quite unpopular. But I would definitely look that up.
People who make the tools that do all the special effects, all use this Python to do exactly the sort of thing you want.
Thank you. Thank you. Yeah. That's kind of my current project at the moment, so I'm just looking into that. But yeah, I'm finding it so much more useful than writing it myself and finding it's all broken. The front?
Say AMReX is for modern Fortran. Roughly how much of the Fortran out in the wild is modern versus not?
I mean, it depends on your field. So my field is a relatively recent field, so people have only really been doing this sort of thing since the 90s and post that. So in my field, most of the code is modern Fortran, but I'm definitely in other fields, you get a lot of Fortran 77 still floating around. So yeah, it's very field dependent.